Hello, and welcome to my cheap, homemade, understandable, minimal processor. This 4-bit TTL processor all begins with the clock pulse. The clock pulse / heartbeat of the computer begins with my 555 circuit. This was mainly covered in my part 1 of the circuit, but I'll quickly go over it now. The initial 555 generates the square wave. The second 555 is responsible for debouncing the user's input. This mode can be selected with the third 555 switch. You will see that the accumulator has halted, and now to increase the program count, I will press. And there we go, it incremented the program count by 1. And on my current program, which is just increasing the accumulator by 1, you see it goes up with each user input. So that leads me nicely to the program that is loaded onto this computer. So, my program from part 1, which was the Fibonacci sequence right here, I do have it loaded fully, although through your comments I realized that this program does not work. So I replaced it for a much simpler program. Here I have it on my computer. I'm just loading the accumulator with a 1, 2, 3, 4, 5, 6, 7, all the way to 14. So now that I've explained what is on the program EEPROM, I'm going to explain how I got it on that EEPROM. That was done with this EEPROM programmer. I made it myself following the Ben Eater tutorial online. And yeah, this is also used to program the control EEPROM. The clock pulse is made available to the circuit over this data line. This data line, or bus, connects to the program counter. The program counter keeps track of the current program that the computer is on. So as you can see here, it is counting, cycling up through the numbers. The current program that it is running is going to run all the way up through 15, and then cycle through again. Many other ICs, such as the address register and accumulator, also need the clock cycle / pulse. This is because they need to be on the same sync as the program count, program EEPROM, and control EEPROM. If they were not on the same sync, they would not know when to update, read information, / receive control codes from the control lines. If I follow the program counter's address lines up into the program EEPROM, you can see that they feed into the EEPROM's address pins. The address pins determine which segment of the program EEPROM it needs to grab to display on its outputs. As the address changes, increments upwards, you see the data change on its outputs. The data currently loaded onto this EEPROM is visible above here. You can watch the readout of the data on these LEDs correspond to the 1s and 0s on the screen. From there, the program EEPROM outputs are entered into the control EEPROM's inputs for the address lines. This is so that way the control EEPROM can grab the corresponding control codes that must be sent into the ICs. From there, the low nibble of this program EEPROM's data output is made available on the MUX. And because this program is calling for it to just be a constant, it's going to the MUX is going to output the program EEPROM's low nibble right into the ALU. The MUX also has the option of using the inverted RAM as a input to send into the ALU. The other input, the B, is always going to be coming, the A is always going to be coming from the accumulator. So that way you can compare either, you can send just from your program through the MUX to the ALU into your accumulator, or you can compare your program EEPROM to your MUX versus what was stored in your accumulator in the ALU. So now that we've covered what the MUX, ALU, accumulator, RAM, and inverted RAM controls, I'm just going to go over what the address register and this NAND is for. So this address register will send the new address if we're calling for a go-to command into the program counter. What's determining that program counter jumping to the new address, it's controlled by this NAND gate. This NAND gate has one of its nodes connected to an AND of the first two binary bits of the low nibble, and then the other node of this NAND gate is connected to the ALU's A equals B pin. And that way, when those through NAND logic, it controls the load, and the load is what controls if a new address is going to be pushed through the program counter.